So, just like we did for Cartesian coordinates, we will do it the same way for cylindrical coordinates as well, except that the structure of the equations will change. So, in the Cartesian coordinates we were dealing with the situation that del square phi was equal to 0, right. So, now instead of writing it this same equation in Cartesian coordinates, if we write it in cylindrical coordinates, this is what we will end up with, right. Del square phi del z square plus del square phi del r square plus 1 by r dot del phi del r plus 1 by r square del square phi del theta square. Okay. Now, if you look at this water jet that is coming out of the stream that is coming out of your faucet, right. Let's consider a situation where you have this horizontal jet, the radius of the jet is r, right, or actually for in this case we will call the radius of the jet as a. Okay. So, if I were to take the cross sectional view, that is the radius of the jet, right. And so, in my r theta coordinates, this is my r direction, this is my z direction, and this is my theta direction, right. Now, if this jet were to develop some kind of instability, I would have the instability on the jet look like this, right. And so, this would be the lambda, okay. And then at any location, I am sorry, I made a mistake, this should be z and this should be r, okay. And so, at any location z, this would be the value of eta, right, the amplitude of the disturbance. And of course, your liquid is moving with a velocity ul, okay. And we make the same assumptions, it is a inviscid incompressible flow, and then there are small instabilities. So, therefore, I am applying a linear stability theory, and then once again my k is equal to 2 pi by lambda. Okay. So, now if I look at it in the circumferential direction, just like I have a instability in the z direction, I can also have a instability in the circumferential direction. So, I could have ripples on the jet along the circumferential direction as well, isn't it? Just like there are ripples in the flow direction, I could have ripples on the circumferential direction for the jet. So, at the minimum, at the least complicated solution that I can think of is where the phi has a form where I have one part of the function being a function of r and theta, the other one being sinusoidal in z, and then e to the power of minus I omega t. Okay. So, if I substitute this back in the mass conservation equation, del square phi equal to 0, I will end up with minus k square times phi plus del square phi del r square plus 1 by r del phi del r plus 1 by r square del square phi del theta square equal to 0. Okay. So, if the number of ripples in the theta direction is s, all right. So, I said, so how many, so what is the value of s in this figure? How many ripples are there? How many peaks are there? 5. So, in this case I have an instability with a s is equal to 5. Okay. So, similarly I can, if I have a perfect cylinder, s is equal to 0. Okay. If I have a shape like this, s is equal to 2, right. Similarly, I can have 3 peaks, this is s is equal to 3, and I can have this is the instability with s is equal to 4, isn't it? Okay. So, now I can write this same equation, and instead of with phi 1 I now break it up into 2 components. So, I am going to make my phi 1 r theta to be equal to phi 2 r times cos of s theta, right. So, in that case my potential function will take the form phi 1 r or sorry phi 2 r times cos of s theta cos of k z and then e to the power of minus I omega t. You all with me on this? Okay. But at the end of the day we are doing this whole exercise because we want to express k as a function of omega, right. That is the whole objective of doing this analysis. Now, if I go back and substitute all these equations in the mass conservation equation and I solve for it, I will end up with a solution so this, if I substitute it back in the mass conservation equation, what I will end up with is an equation that looks something like this. Okay. It is r square d2 dr square of phi 2 of r, okay, plus r times d dr of phi 2 r plus s square plus k square r square times phi 2 of r is equal to 0. Now, this form of this differential equation is a very classical equation. Okay. The solution of this equation generates what is known as Bessel's functions. How many of you are aware of Bessel's functions? Come again? Read a little bit about Bessel's functions. Okay. So, Bessel's functions has very interesting properties or what are known as modified Bessel's functions, I am sorry. And so, you get modified Bessel's functions of first kind and modified Bessel's functions of second kind and so on. Okay. So, I will not get into the details of Bessel's functions, and the derivation is a little complicated, and in the interest of time I am skipping it, but you follow the same procedure as we did for Taylor instability or Helmholtz instability, which is you integrate the momentum equation, you set the del phi, del z equal to your del u del t or del eta del t, and then you derive the constants, right, the coefficients. So, if you go through the whole exercise just like we did for, and it is there in the handout, if you want the full details of how things were developed, you can look it up in the handout. And in this particular case, if you remember, when we were dealing with Cartesian coordinates, we had only one radius of curvature. But in this situation now, I have two radii of curvature, right. I have one radii of curvature along the z direction. So, this I will have one r1 corresponding to this, and then I will have another radius of curvature corresponding to this. Okay. And so, the first radius of curvature 1 by r1 is given by 1 by r minus 1 by r square. Okay. And in the case of the second one, the 1 by r2 is given as minus del square eta del z square. Actually, I take it back. So, this is r1 and this is r2. Okay. And so, if you substitute all these equations, you end up with a dispersion relationship, and so the dispersion relationship looks something like this. Okay, let me write it out. Okay, so the dispersion relationship looks something like IS K A divided by IS prime K A. I will come to what do I mean by IS and IS prime, times minus omega square, and you will end up with rho L minus rho G divided by rho L plus rho G times G by A, okay, and then times K A minus sigma divided by A cubed times K A times 1 minus A square minus K square A square. Okay. So, this IS is known as the modified Bessel's function of the first kind. Okay, and just like you look up the sin x and cos x values in a table, you can look up these values. Okay, it is derived using gamma function. Okay, so, our definition of IS of x is equal to I to the power of minus s Js of Ix, where Js is your regular Bessel's function, right, not the modified Bessel's function, and that is given as m equal to 0 to infinity 1 divided by m factorial gamma function of m plus s plus 1, and then x divided by 2 to the power of 2m plus s. Okay. So, this gamma here is the gamma function. Okay. So, mathematical details aside, let us now see what the solution will look like. Okay. So, let us look at, now that I have this whole equation over here, let us look at some specific cases. Let us look at the first case, which is the most simple case. okay, when G is equal to 0 and S is equal to 0, which is a cylindrical jet. Okay, so, for a cylindrical jet, if you make your S is equal to 0 and your G is equal to 0, okay, then I end up with a situation, and I am looking at the case when omega is equal to 0, okay, the critical wave. So, in that case my k square a square is equal to 1, or my neutral wave is just the inverse of the radius of the jet. Okay. Okay, I made a mistake. I think there is a bracket here. Okay. Yeah, I think that takes care of things. Yeah. So, when G is equal to 0, this term goes away, and then your your S goes away. So, your 1 equal to k square a square. Okay. So, or in that, what that means, your critical wavelength is 2 pi a. That is a very interesting observation, that your neutral wavelength corresponds to the circumference of the jet. Okay. Now, I want to figure out what is the most dangerous wavelength in this case, right. So, I do a d omega dk equal to 0, okay, and that will end up being a very complicated equation for which there is no closed form solution. You have to solve it numerically. Okay. So, if you do a numerical solution, the answer comes out that your k d times a whole square comes to equal to 0.4858, or effectively 0.5, let us say. Okay. What that means is your lambda d is equal to 9.016 times a, or roughly 9 times a. What does this mean? Okay. It means the most dangerous wavelength, that lambda, is 9 times, approximately 10 times the radius. Okay. So, when you see the ripples in your faucet, it is going to be very close to 10 times the radius of that jet. Okay. Which means, if you have a really thick stream of water coming out, unless you give it sufficient length, you will not see it break up. But if you do a really tiny amount of flow rate, that you have a very thin stream coming out, that is more likely to break up into droplets in the amount of distance you have from the faucet to the bottom of the sink or the top of the sink, right. Okay. So, you will see that as you keep reducing the flow rate in your faucet, at some point it will start breaking up into individual droplets. Now, the question is, how far does the jet have to travel in order for that first droplet to form, right. We will come to that in a minute. Okay. But before we go there, the other thing I want to find out is what is the growth rate of this disturbance, the maximum disturbance, right. So, if I think about it, my k d times a whole square equal to 0.5, which means that my k d is roughly equal to 0.7 by a, isn't it? Okay. So, now I define my omega naught square, my non-dimensional frequency, okay, to be equal to sigma divided by rho L by rho G times A cubed. Okay. And I write down my dispersion relationship in a non-dimensional form. So, I have omega by omega naught square, that is equal to 1 minus k square A square times K A times I S prime K A divided by I S K A. And I am going to use a mathematical identity. The mathematical identity is the derivative of this modified Bessel's function takes this form. Okay. And for KD times A equal to 0.7, if I substitute this value of KD times A equal to 0.7 in this equation over here, okay, I end up with a solution that says minus omega by omega naught square comes to about 0.13. Okay. So, in other words, your I times omega d comes to about 0.34 omega naught. Okay. Now, I can define a wave velocity C d corresponding to the magnitude of omega t divided by k d. Okay. And if I substitute all the values that I have gotten so far, what I will end up with is the group velocity that looks something like this. So, I end up with C d is equal to 0.34 times omega naught square times omega naught divided by 0.7 divided by A, that is my omega by k d, right. And so, I end up with a value that is approximately half times sigma divided by rho L plus rho g times A to the power of half. Now, in order for this relationship to be valid, the value the velocity of your jet has to be much bigger than the group velocity of this disturbance. Okay. Or in other words, your UL divided by CD has to be much greater than 1. Okay. That is the implicit assumption in this derivation. Or in other words, UL times rho L plus rho g times A divided by sigma to the power of half has to be much greater than 1. Okay. Now, that is one constraint. The other one I want to find out is how much time does it take and how much distance does it take before this jet will break up into droplets, right. So, let us assume that the time taken by the droplet to travel a certain distance before it breaks up. So, it will time Tb is the time it takes the disturbance to grow from a very small value from a value of delta naught, a very small value, to the jet radius A. Because once this disturbance goes to a value of A, that is when it is going to break, right. So, in other words, if I write it down, it is delta times e to the power of omega d times TB should be equal to A. Okay. In other words, my TB is equal to 1 divided by the magnitude of omega d times log of A by delta naught. Okay. Now, I made this assumption that the constraint on this whole thing is that UL should be much bigger than CD, right. Let us for simplicity assume that UL is some multiple of CD, right. So, in other words, UL is some multiple of sigma divided by rho L plus rho G times A to the power of half. Okay. So, then the distance Z that it travels before the jet breaks up is then equal to UL times TB, isn't it? Okay. So, let us assume that this delta, the initial magnitude of the delta is very small. Let us say it is 1000 times smaller than the jet radius. Okay. So, if to begin with my delta naught is let us say about 10 to the power minus 3 times A. Okay. So, then my ZB will become equal to 1 by omega d times log of 10 to the power minus 3, isn't it, or 10 to the power plus 3 essentially, because delta naught is in the denominator. And so, in essence this is equal to 3 divided by 0.34, and omega d we said was, what did we say omega d was? Omega d was 0.34 times omega naught, and what was omega naught equal to? Let us see, we wrote down omega naught somewhere, right? That is omega naught, right? And so, you have to multiply this by 0.34 and substitute it here. Okay. So, in essence this becomes equal to 0.34 times UL by A, because omega naught is UL by A, isn't it? And so, this value comes to let us see, and this times UL essentially. So, the ULs cancel out, and therefore, the value of ZB that we get is, if you do the math on this one, this comes to about 11.7. No, sorry, this comes to about 8.8, I am sorry, 8.8 times A. That is assuming that your delta naught is approximately 10 to the power minus 3 times A. Now, if I assume that the delta naught is even smaller than that, if it is 10,000 times smaller than A, then the value of ZB comes out to 11.7 times A, or in other words it has to travel something like 9 to 12 times the jet radius before it breaks up into droplets. Okay. So, from a simple linear stability analysis we can sort of estimate how long it has to travel, what distance it will travel before it breaks up into droplets. Okay. Now, the other case we are going to look at is a film boiling on a cylinder. Okay, we are going to apply this instability theory for cylindrical heaters. Okay, so, if you remember, I showed this natural convection equations yesterday, right, the solution, and if you remember, for a natural convection in a cylinder, if I have a cylinder that looks like this, the boundary layer that forms around a hot cylinder it sort of looks like this, right? And I said that the last 30% is virtually insulated. Remember we had this discussion yesterday. So, just like you have the boundary layer profile around a hot cylinder, in film boiling also the vapor film looks something like this, very similar, okay? Except that is how the vapor bubble looks like in film boiling. Okay? So, the value of S that corresponds to a shape like this, that fits, if you do a best fit for a shape like this, S is equal to 1 by root 2. If I substitute S is equal to 1 by root 2 in my Bessel's function solution, I get a shape that looks like this, okay, very similar to a film boiling bubble shape. So, the next case we are going to look at is, instead of S being equal to 0, I am going to look at what happens when S is equal to 1 by root 2. Okay, and in this case I cannot assume G is equal to 0, G is not equal to 0 in this case. Okay. So, if I look at the equation now, the equation becomes a little bit more complicated. Okay, the equation looks something like this. Okay, and then I will have the second term, which is sigma divided by A cubed times half minus k square A square, because I have 1 minus S square. So, 1 minus half becomes half, and then I have K A divided by rho L plus rho G, and then I have the modified Bessel's functions. Okay, so, for case 2, if I want to derive the critical condition, which is omega is equal to 0, and I am trying to figure out what is my Kc equal to. Well, the solution comes something like this. So, I get Kc square is equal to 1 by 2A square plus 1 by L naught square, okay, and that is equal to 2 pi by lambda c square, or in other words, my lambda c becomes equal to 2 pi times L naught 1 plus 1 by 2 r prime square, okay, where my r prime is equal to r divided by L naught, or you can also say A divided by L naught. My r is equal to A in this case, the radius of the cylindrical heater. Now, there is a particular reason why I wanted you all to look at this equation. Okay, remember I said the diameter of the size of the heater affects your heat flux in boiling. Okay, so, if you look at it philosophically, this tells you that you got to worry about the size of your heater. Okay, why so? If it is a very large cylinder, then my 1 by r prime square goes to 0, isn't it? But what if it is a thin wire? Okay, then this is a big number. In other words, your lambda c will become larger as you start shrinking the diameter of your heater. In other words, the spacing between the bubbles will keep increasing. The diameter of the bubbles will keep increasing, and if the diameter goes up, then the frequency goes down. Okay. So, when you are designing your boiling heat transfer experiment, now you got to figure out what diameter heater should I use. Okay. Now, the more fundamental question becomes, at what value of R does my lambda c become independent of the diameter of the heater? That is the large heater, isn't it, where the heater size does not affect your heat flux, and there is a critical value below which the diameter of your heater starts affecting your heat flux, isn't it. Okay. So, let us figure that out. Actually, before I go there, let us finish the instability analysis, and then we will go into the large cylinder, small cylinder, large heater, small heater limit. Okay. So, we just derived the critical condition, but we also got to derive the maximum wavelength situation, the maximum growth rate situation. Okay. So, what is the maximum growth rate? Well, so I am trying to figure out my omega d and my lambda d, right. So, I am going to do d omega dk and set it equal to 0. So, if I do that, what I end up with is sigma divided by 1 by 2a square minus 3 kd square is equal to 0, or in other words, my 3 kd square is equal to 1 by L naught square plus 1 by 2a square. Okay. And for a cylinder where your R is equal to A, then my lambda d is equal to 2 pi root 3 L naught times 1 plus 1 by 2 r prime square to the power of minus half. Actually, I missed a minus half here, I am sorry. There should be a minus half over here, I missed that. Okay. And same thing when I am writing something as r prime, what I mean is r prime is equal to r divided by L naught or a divided by L naught. Okay. So, then the more fundamental question is whether I am dealing with lambda c or whether I am dealing with lambda d. There is one value of r at which it becomes independent, isn't it. So, in other words, I want my 1 by 2 r prime square to be much less than 1, let us say 0.1 or 0.01, so that this side becomes the same as a flat plate, isn't it, where it becomes independent of the size of the heater. Or in other words, I want my r prime, I am sorry, 1 plus this sorry, actually, yeah, this one, or otherwise I want my r prime, let us see, to be greater than 0.5 r prime square, isn't it, which means I want my r prime to be greater than 0.7, or in other words, my r should be bigger than 0.7 L naught. So, how much did we say was the L naught for water? Do you all remember? L naught is equal to sigma divided by rho L minus rho g times g, square root of that. So, we said lambda d is equal to what, 25 millimeters, and lambda d is equal to is equal to 2 pi root 3 L naught, right, or roughly equal to what, 11. What is 2 pi root 3? About 11. Can somebody calculate and tell me? Right? So that's 11 times L naught, or L naught is roughly about what, 2.2 millimeters. Yeah. Which means my radius for water needs to be 0.7 of this, so about 1.5 millimeter. Does that make sense? Okay, we will revisit this topic once more, all right, when we get to maximum and minimum heat flux in boiling. But so the next thing we want to do is we want to predict the maximum heat flux we can get. Okay. Now there is a little bit of controversy in terms of the minimum heat flux. Okay. But before we get into the controversial situation, let us do an estimate for Q max, okay, in critical heat flux. So as I mentioned, okay, in critical heat flux, what do I have? The vapor bubbles merge, and it moves up with a velocity of ug, and the liquid is coming down with a velocity of ul. Okay, and then on top of that I am forming ripples on this vertical jet that is forming. Okay. So I do not know what the diameter of this jet is. Let us just assume that the area occupied by the jet is Ag. Okay. And if I know the number of jets per unit area, okay, then I know the number of jets that are there in a square unit. Okay. Or I can divide the total area of the jet by the total area of the heater, and I can get a ratio, right. So in other words, I can write down my Q max to be equal to whatever is this critical velocity of this UGC that comes from Helmholtz, instability, times the area of the jet, right, times rho g gives the total mass flow of the vapor that is leaving the heater surface, right. And so if I multiply it by the HFG, that tells me the total latent heat taken away by the system, and that should be equal to my Q max double prime times the total area of the heater, isn't it? Yeah. Or in other words, my Q max double prime is nothing but UGC times rho g times HFG times Ag by At. Okay. Now, what is my UG minus UL, that critical velocity, how much is that? Well, it is 2 pi lambda c let us see, actually let me take a step back. So, my UG minus UL, this critical velocity we derived was equal to sigma divided by rho g times radius of jet, right. Actually, let me take a step back before we get there. What did we derive from Helmholtz instability? We said that this UG minus UL, this critical value, was equal to sigma times Kc times rho L plus rho g divided by rho L rho g, right, square root of that. That is what we had derived. And my Kc is nothing but 2 pi by lambda c. So, in essence this becomes 2 pi sigma divided by lambda c times 1 by rho L plus 1 by rho g. Well, rho L is something like 1000, rho g is something like 0.5. So, I can neglect this 1 by rho L, it does not really contribute anything. Okay. So, if I, and then the other thing we derived was from the cylindrical coordinates was lambda c was equal to 2 pi a or 2 pi radius of the jet. If I look at it, this is the radius of the jet, isn't it? And we said that the critical instability was the circumference of the jet. Remember that, right? So, if I substitute it, then the critical value UG minus UL then becomes 2 pi sigma divided by 2 pi radius of jet times 1 by rho g. I am neglecting rho L. Okay. So, in essence this simplifies to sigma divided by rho g times radius of jet. You all with me on this? Now, Zuber, when he was deriving this equation, he made an assumption. Okay. The assumption he made was that during critical heat flux I form all these jets, the columns, right. So, he assumed that these jets were located in a sort of a square grid. Okay. And in these square grids, if the radius of the jet is Rj, he assumed that they were spaced 4 Rj apart. Okay. So, in that case the area occupied by the jet divided by the total area of the heater becomes pi times Rj square divided by 4 Rj square, and so that comes out to pi by 16. Okay. But Zuber could not make up his mind whether this Rj is equal to lambda c by 4 or whether it is lambda d by 4, assuming this is lambda, this is the spacing between the jets. So, this lambda could be either lambda c or lambda d, we do not know which one it is. Okay. And if you do a mass balance, the amount of vapor leaving the surface should be equal to the amount of liquid coming to the surface, isn't it? Okay. So, if I do a mass balance, then rho g times Aj times Ug should be equal to minus rho L times A of the heater minus A of the jet times UL. Okay. So, in that case your UL becomes equal to pi divided by 16 minus pi with a negative sign times UG times rho G, let us see, rho G divided by rho L, and so then your UG minus UL becomes equal to the critical value, that becomes equal to UG plus pi divided by 16 minus pi times UG times rho G by rho L. Okay. And so, if I substitute it in my instability theory equation, that should be equal to 16 divided by rho G times radius of the jet, the whole square root. Okay. Or in other words, my Q max let us see. So, if the radius of the jet is, or if the area of the jet is AJ, that times UGC is the volume flow rate, that times rho G is the mass flow rate, that times HFG is the latent heat I am taking with me, okay, and that should be equal to my Q max times area of the heater, right, the Q double prime max times area of the heater. And so, if I substitute for UG from this equation, okay, and try to do this calculation, I will end up with a Q double prime that looks like a constant times rho G HFG times you get a sigma times G times rho L minus rho G to the 1/4 power, and then you get a rho L plus rho G divided by rho L minus rho G to the power of half. Okay. And different authors have come up with different values of this C1. Okay. So, according to Zuber, this value of, and then there was a correction factor, let us call it as CF. Okay. So, according to Zuber's calculation, this C1 will be rho L times 16 minus pi divided by rho L times 16 minus pi plus rho G times pi. So, realistically this value of C1 is approximately equal to 1, right, because rho G is so small it does not really matter. And this correction factor CF, Zuber could not make up his mind. Okay. This correction factor CF is equal to 0.12 if you use lambda d, and is equal to 0.16 if you use lambda c. Okay. And the mean value of this CF is something like pi by 24. Okay. So, that helps us figure out. So, in other words, I can write this equation, just put a pi by 24, this one goes to 1, and that is my maximum heat flux in boiling. Does that make sense? Okay. Now, I want to use the same type of procedure when it comes to minimum heat flux. Okay. So, when I am trying to do the minimum heat flux, there is a little bit of a controversy. Okay, so let us come to the controversial part. Okay, so when I am doing the minimum heat flux, let us look at how the vapor pattern looks like. Okay. So, in the first half of the cycle, okay, we will have bubbles that are that are departing from the surface. Okay, that is how the profile looks like in film boiling in the side view. In the second half of the cycle, okay, so what was the intervening space between the two bubbles, that generates a bubble, and wherever you had generated a bubble, that becomes the intervening space. Okay. Or in other words, if I look at it from the top view, okay, if I had a bubble that was formed in the first half of the cycle, in the second half of the cycle, that will become the trough, isn't it? And I will form a bubble here, here and here. Does that make sense? But then the big question is, do I form a bubble in the center or not? Okay. So, since I am doing a 2D instability, this is my lambda d for a 2D instability, isn't it? Right? Because I am assuming my wave propagates both in the x direction and in the y direction, right. If I have an instability going in this direction, I will have a peak and a trough, isn't it? And then in the next cycle, the peak becomes the trough and the trough becomes the peak. Similarly, in the y direction, I will have two peaks, and in the next half cycle they become the trough and this becomes the peak, right. Now, the question is, how many bubbles am I generating per unit area? Okay. So, why do I care? Because if I write down my Q min, okay, my Q min is nothing but the volume of the bubble at departure times rho g, that gives me the mass of the bubble, times HFG, right, that tells me the energy in one bubble, times if I know the frequency at which the bubble departs, that gives me the power, and then at the end of the day I need to know the number of bubbles per unit area, isn't it? So then the big question is, how many bubbles am I generating per unit area? Now if this model is valid, how many bubbles am I generating? Okay, forget the red ones. Okay, so how many do I have? I have 1/4, 1/4, 1/4, 1/4, right? 1 in the first half cycle, and then I have 1, 2, 3, 4 times half, so that's 2. So that means I am generating 3 bubbles per cycle. Yeah, but if I take this model to be valid, where I include this red guy, then I am generating 4 bubbles per cycle. Okay, so there was one school of thought that said that there are 3 bubbles per cycle. There was another group of thought that said no, there are 4 bubbles per cycle. And when Zuber did his analysis, okay, he assumed there was 2 bubbles per cycle. Okay, even though if you are faithful to the model he assumed, the correct number should be 3. Does that make sense? Okay. So there was a seminal paper that was written by Cernas. Let me pull up that particular paper. Unfortunately, I can't find it right now, but in any case, what Cernas, and there was a paper written by Cernas and his co-authors. Okay, where they argued that in real life it's not a 2-dimensional instability, it's a 3-dimensional instability. Okay, so if you include a 3-dimensional instability, your heater configuration is actually this. And that is lambda 3D. Okay, and you can see lambda 3D is nothing but lambda 2D divided by root 2. So if you take this model of Cernas, then you are generating 4 bubbles per lambda 3D square or 2 bubbles per lambda 2D square. Okay, or in other words, this value of n is equal to 2. Make sense? Okay, so that resolved this controversy that went on for about 5 years in terms of what is the correct grid size. Okay, so in that case, my VB will be equal to 4/3 pi r cubed, and r is nothing but lambda 2d by 4 cubed. Okay. And so if I go back and substitute these values, but the big question is, what is this frequency f? Okay. Now, what Zuber did, which was a little erroneous, but it actually ended up giving him the correct answer. Sometimes you make two mistakes and you end up with the correct answer, right. So, he took a very weird approach. He said that I am going to calculate the average rate of this d eta dt. Okay, I am going to calculate the average. So, what is a mathematical kosher way of calculating this d eta dt? I would take 1 by t, the time period, go from 0 to t, take d eta dt, integrate it with dt, right. That is the correct way to do it, is not it, because my eta is equal to eta naught e to the power of I omega t. And I already know this omega is nothing but the most dangerous wavelength, is not it. But Zuber did not do it that way. He did the average in terms of space, not time. Okay. So, he said I am going to calculate d eta by dt, and he said that when a bubble grows to about 0.4 times the lambda d, that is the point at which it departs. He arbitrarily assumed that based on his experimental images. Okay. So, he said I am going to average it over a distance of 0.4 lambda d2 or lambda 2d, and I am going to go from 0 to 0.4 lambda 2d. I am going to take this d eta dt and integrate it over d eta. Okay. So, if you do that, then your average growth rate comes to about 0.2 times lambda 2d times minus omega I or omega d. Okay. And then he said, well, then the time period tau is the bubble diameter at departure divided by this average value of d eta dt. Okay. And so, well, the bubble diameter at departure is lambda d2 or 2d, and this comes to 0.2 lambda d2 times minus omega naught, and so that comes out to equal to 5 divided by omega naught. So, your frequency becomes 1 by tau, or that is equal to 0.2 times omega d. Okay. So, if you substitute all these values in the original equation, then your q min comes to equal to some constant times rho g hfg times root of sigma g rho l minus rho g divided by rho l plus rho g whole square. And if you follow the procedure of Zuber, this c comes out to equal to 0.18. Okay. But this is actually wrong. From experiments, people find out that this c comes to about equal to 0.09. Okay. Now, so far we have been doing the prediction based on linear stability analysis, but in reality a bubble will follow the linear growth rate only for a certain period of time. Okay, and then the amplitude of the disturbance becomes almost the same size as your wavelength, and so you cannot use linear stability analysis anymore. Okay. So, if you look at a typical experiment and if you plot your actual height of the bubble divided by some assumed initial height of the film thickness, vapor film thickness, and if you plot it in terms of omega d times t, okay, that is your non-dimensional time, this is your non-dimensional disturbance height, right. according to linear stability analysis, this should be a straight line, isn't it? Okay, if I do a log plot, essentially, if I take the log of this guy, because eta is equal to eta naught e to the power of minus omega dt, right? But in reality, if you plot the experiment, you will see that it will follow the linear line only for up to a certain limit, and then it will actually become slower. Can you guess why it becomes slower? Well, part of the reason is initially the vapor bubble grows like a grows until it becomes almost like a half circle, and beyond that point the bubble actually starts growing sideways instead of growing up. Okay, so it becomes a non-spherical shape at certain point in time, and usually that's the point at which you see the departure from the linear stability prediction. Okay, so so there are some criticisms to the way that Zuber derived this equation. He did this average of d eta dt. I actually forgot to put the bar here. So this average value of d eta dt that he calculated, he did it over space. In reality, he should have done it over time. Okay, but even with those mistakes, you realize that he came very close to the correct number, and that's the amazing part. And do you all know where Zuber got his PhD? Zuber actually got his PhD at UCLA. Okay, so but any case, so that's the maximum and minimum heat flux in boiling. Okay, so let's take a quick break for about 10 minutes. And then we will come back and look at cylindrical, the maximum and minimum heat flux on a cylindrical heater. Okay. All right. Good afternoon. So the next thing we are going to look at is, what does a maximum heat flux and minimum heat flux look like on a cylindrical heater. Okay. So before we go there, in the previous session, I was talking about this controversy in terms of the number of bubbles being generated per units heater area, right? So let's see, the paper by Cernas, I was able to find it out. So here is a very nice schematic from that paper. Here is the paper. Taylor wave configuration for boiling from a flat plate. And so if you look at the essential summary of their argument, so what they are saying over here is, the format that Zuber looked at was this. Okay, what is peak in the first cycle becomes the trough in the next cycle. Okay, so these becomes the crosses, and these become the dots essentially. But the big question is, do I have a bubble in the center or not? Okay. And so Zuber assumed that this was lambda 2, and what Cernas said was, well, no, this should be actually lambda 3. Okay, and it turns out lambda 3 is equal to lambda 2 divided by root 2. Okay, and so if you make that assumption, then there are how many bubbles are there? Half of these 4, that makes it 2. And let's see, and well, if you look at it in terms of the lambda 3, then there are a quarter. Let's see, so this would be your first configuration. Okay, so you have one bubble in the center and no bubbles around it, right? And then in the next half of the cycle, you have a quarter of each of these guys. So that makes it 1. So you have 2 bubbles per lambda 3 square, or 4 bubbles per lambda 2 square, and they are the same. Okay, so that's how they were able to resolve the controversy, and they said n equal to 2. And if you go through that paper, it's only a 1-page paper actually, a paper that's only 1 page long. And towards the end of the paper, they make the argument based on experimental data. Okay. So, anyway, so that is one thing I wanted to show you. So, now let us get into maximum heat flux on a cylindrical heater instead of a flat plate. Okay. So, we are going to look at two different limits. One is the small heater limit, the small cylinder, and the other one we are going to look at is the large cylinder. Okay. So, the very basics of it is I have a cylindrical heater and I am going to form jets or columns of vapor, and the diameter of that jet is 2 times Rj. Okay. And there is a spacing, certain spacing, let us call it L, between the jets. Okay. So, for small spacing, for small heaters, this L is equal to lambda 2d or lambda d essentially, let us call it just lambda d. All right. And if I look at it in the cross section of the heater, I will form a heater and then I am going to form bubbles around the cylinder that are going to rise up, right. They are going to slide around the heater and rise up. Okay. So, and at the very heart of it, what we are solving is my Q max in this situation is whatever is the area of the jet or area occupied by the jets times UGC, that gives me the volume flow rate, that times rho g gives me the mass flow rate, that times HFG gives the net energy loss, and so Q max times and that divided by the total area of the heater, that should give me the Q max, right. So, the big question is what is this ratio of Ag by At, what is this ratio? Okay. So, if I look at it, the diameter of this heater is 2R, 2Rj, but if I assume that the thickness of this vapor bubbles is delta, this is equal to 2 times Rj plus delta, right. So, that would be the diameter of the vapor column that is rising from the heater, isn't it. So, in that case my Ag by A will become equal to pi times R plus delta whole square divided by the surface area of the heater, which is 2 pi R times L. So, for a small cylinder we assumed that the L was equal to lambda d. Okay. So, in that case my Ag by A will come out to equal to pi times R plus delta whole square divided by 2 pi times lambda d. And what did we say was the lambda d for a cylindrical configuration? Okay, we said lambda d is equal to 2 pi root 3 L naught times 1 plus 1 by 2 R prime square to the power of minus half. Okay. And what did we say was UGC? We said UGC is equal to sigma divided by rho g times Rj, right, root of that, or in this case Rj is nothing but R plus delta. So, sigma divided by rho g times R plus delta. I still do not know what this value of delta is. Okay. And So, Lienhard and Dheer, they did some experiments and they found that this delta by r, which is equal to delta prime by r prime. So, by delta prime I mean delta by L naught, and by r prime I mean r by L naught. Okay. And so, they found that this value is equal to 3.72. This is a experimental correlation divided by r prime minus 1. So, if I substitute all these equations in this master equation over here, okay, I end up with a equation that looks like q max cylinder for a small cylinder divided by q max Zuber for a flat plate, okay, and that comes to equal to 0.94 divided by r prime to the power of 1/4. Okay. Now, if I look at the large cylinder limit, in the large cylinder limit, my UGC is equal to, sorry, how do I get this out? Come again? Menu button? Okay, all right, good. All right, so in this particular case, what they assumed your UGC was is equal to, okay, that button, okay. So in that other case, they assumed this lambda d was, this UGC was root of sigma k by rho g, okay, and or kd essentially. And so UGC basically, if you substitute your lambda d is equal to 2 pi root 3 L naught, then your UGC comes equal to 1 times 3 to the power of 1/4, and then you have the 4th root of sigma g rho L minus rho g divided by rho g square. Okay. And in this case, what they assumed was this L was equal to 4 times Rj. Okay. So then your Ag divided by A becomes equal to pi times r plus delta square divided by 2 pi r times 4 times r plus delta. So if you see the contrast, when it was small cylinder, this Ag by A was based on lambda d, okay, but in this case instead of lambda d I have 4 times r plus delta, okay. That was the difference. The second difference is they did experiments and they found that for large heaters typically your delta is equal to 1/4 of r, okay. So if you substitute these values and you find out the value of q max, you get q max cylinder for a large cylinder divided by q max Zuber, which is a flat plate, and that came equal to 0.9, okay, because it is independent of the size of the heater for large cylinders, isn't it? So then the question is, at what point do I call a cylinder large cylinder and at what point do I call a cylinder a small cylinder, right? So if I plot these two equations, okay, so in other words, if I plot my q max, okay, so if I plot my q max cylinder divided by q max Zuber, and on the x axis I plot r divided by L naught or r prime. Okay, so what I will see is I will see a graph that comes down like this and then becomes 0.9, right. So there is this critical value of your cylinder radius, beyond which as I keep shrinking the diameter of the wire, the heat flux keeps increasing, isn't it? And then beyond this limit it becomes independent of the heater size. So this is my large heater regime, and this is my small heater regime, where everything else remaining the same. As I keep shrinking the size of the heater, the heat flux keeps increasing. Okay. So then the question is, when does a heater become a large heater? Okay. And so in one case I assumed this L was equal to lambda d, right, and in the other case I assumed the L was equal to 4r plus delta, isn't it? So when my lambda d is equal to 4 times r plus delta, that is the limiting value of r, okay, and in this case my delta is equal to 0.24 r, isn't it? So if I substitute all these values, what I get is a value of r prime that is equal to 2.2. Okay. So in other words, if your r by L naught is greater than 2.2, it is a large cylinder. Okay. So in other words, when I did this plot, a value of 2.2 is where I will see, if I go a value of r being less than 2.2 L naught, okay, I will see the heat flux will keep increasing as I reduce the diameter of the heater. All right. Now let us do the same analysis, but let us do this for minimum heat flux on a cylinder. Okay. And then I will close with a flat plate. In the case of flat plate also, you also have a similar situation, especially when you are doing electronic chip cooling, because now the size of the chip and the boiling on the top of the chip, that boiling heat flux will depend on the size of your package of your chip. Okay. So then the big question comes in, when is the chip a large heater, when is the chip a small heater? Okay, we will come to that. Yeah, go ahead. You have a question?
Why do we assume the bubble diameter is constant?
I didn't get your question.
In this derivation, we have assumed the bubble diameter as delta, that is constant throughout the pipe.
Yes, the bubbles that are nucleating on the bottom surface of the heater. That is the departure diameter, right. So departure diameter, remember I did the analysis in the morning where I did the buoyancy force and the surface tension force, and when the buoyancy force is equal to the surface tension force, the diameter of the bubble comes to approximately some multiple of L naught, right. So the departure diameter is almost constant. It changes a little bit, but it is not very sensitive to superheat. The departure diameter is a little less sensitive to what your superheat is. Okay. So the departure diameter tends to remain constant, and so therefore your bubble diameter that we assume that value of delta, that tends to stay constant. Does that answer your question? Okay. All right. So when it comes to Q min, we can do a similar analysis. Okay. So I'm saving this graph because this is for Q max. This is a graph for Q max, and we will do a similar graph for Q min. Okay. So I am saving this paper. Now when it came to minimum heat flux, the equation I am going to use is Q min double prime is whatever is the rate of generation of vapor bubble, volume flow rate of vapor bubble, okay, times rho g times HFG and then that is divided by the area of the heater, which is 2 pi r times lambda d. Okay. So, I in the interest of time I am skipping the steps, but in essence what Zuber ended up was let us see. Zuber ended up with a equation that looks something like this. Okay. So, q min double prime for a cylindrical heater, it came out to something like 0.06 rho g HFG sigma times g times rho l minus rho g divided by rho l plus rho g whole square to the power of 1/4, and then so this is very much similar to the flat plate equation, but for cylindrical heaters he came up with a correction factor which was r prime square times 2 times r prime square plus 1 to the power of minus 1/4. Okay. Now, for a flat plate, if you remember, q double prime minimum z, that comes to 0.09 rho g HFG sigma g rho l minus rho g square to the power of 1/4. Okay. So, if I do the derivation, then my q min divided by q min Zuber, it comes to 2 by 3 times r prime square times 2 r prime square plus 1 to the power of minus 1/4. Okay. So, if I do a plot just like I did for the q max, if I do a similar plot for q min, so I am plotting r by L naught on this side, which is r prime, and I am plotting q min divided by q min z. Okay. So, I am doing a log plot. Okay. So, interestingly what happens is this is about 0.67. That is how the graph looks like. Actually, let me do it with red. That is how the graph looks like. Okay. And so, what you see is for film boiling, r prime greater than 1 is a large heater. For nucleate boiling, r prime greater than 2.2 is a large heater. Okay. So, what this means is if I were to make an experimental apparatus where I want to measure the heat flux in the large heater regime, and I want to do the experiment both for nucleate boiling and film boiling, then I better choose a diameter of the heater which is greater than 2.2. Okay, because if I do a heater which is more than 1, it will become a small heater in nucleate boiling and large heater in film boiling. So, you will get a very convoluted data. Okay. So, it is important to be aware of these nuances before you start doing your experiment, before you start designing your heater apparatus. Okay. Now, the big question is how about flat plate, because when I discuss the boiling on nanoparticle coatings pool boiling, you will see a lot of literature. As I mentioned on the first day, our group was the first one to generate the boiling curve for both nucleate boiling and film boiling with nanoparticle coatings with carbon nanotubes, right? And subsequent to that, there were a lot of papers that came out. In fact, now there is a Gordon conference on boiling on nanostructured surfaces in Galveston near Houston almost every alternate year. I think there is one coming up this year. So now they have a whole conference around these nano coatings for heaters, and you go and look at the papers. 80 to 90% of the papers will be where they have done experiments on 1 centimeter by 1 centimeter chips. So now the question is, the heat flux that they are measuring, how much of that heat flux is because of the size of the heater, and how much of the heat flux is because of the nano coating, because you end up with a convoluted experiment just like you see over here, isn't it? Okay. Now the big question is, what is the value of lambda d when you have nano coatings? Does the value of lambda d change when you have nano coating? Okay, that becomes the other question too. So what becomes a large heater, because you are comparing your plain heater heat flux with a heater with nano coating. Okay. So for a heater with nano coating, it might be a large heater, but for a heater without coating, it's a small heater, and you are comparing the two, right? So then it becomes a convoluted experiment. The conclusions you are drawing are probably erroneous, because you are not testing both under the same conditions. Does that make sense? Okay. And so if you look in papers in the literature for these nano coatings, a good number of them have this issue. Okay. And I'm going to discuss that more tomorrow and Friday. Okay. But let's get the fundamentals correct. All right. So we can then go back and critique the work that is out there in the literature. Does that make sense? Right. So now the big question is, when I'm looking at a flat plate, at what point does it become a small heater, and at what point does it become a large heater? Isn't it? Okay. So in order for me to do that, let's go back to the paper by Sarnas or Zuber's paper. And when you are particularly close to critical heat flux, when you have these jets that are forming on the surface, right? What did we assume? We assumed that the distance between the jets is 4 times Rj, isn't it? And the radius of each jet is Rj divided by 4, right? But what happens if my heater is less than lambda d? So how much did we say was lambda d? Do you all remember? So we said lambda d is equal to what? 2 pi root 3 L naught. Right? Lambda d is equal to 2 pi root 3 times L naught, isn't it? So typically for water, your L naught is about 2.5 millimeter. Okay. For hydrocarbons, it could be alcohol, it could be refrigerants. This L naught is about 0.7 millimeters. You can substitute the values. That's the value you will get. Okay. And so if you calculate the value of lambda d, which is roughly, actually this is 2.2, I'm sorry. So lambda d is roughly equal to what? We found 11 times L naught, 2 pi root 3 is about 11, right? So that means this is about 25 millimeters, and this is about 77, about 8 millimeters, let's say, isn't it? And come again? Oh, lambda d, sorry. Yeah. Now Dheer and Lienhardt, they did a study in 1975, around that time. They showed that if your heater size L, is less than 5 times lambda d, it becomes a small heater. Okay, they showed that as you shrink the size of the heater, everything else remaining the same, the heat flux starts going up. Okay, so 5 lambda d is the limit based on experimental, and they did some analysis also to support that. Okay, which means that your minimum heater size should be what? 5 times lambda d is what? Okay, 125 millimeter, or roughly 12.5 centimeter, which is what? How many inches is that? 5 inches. Okay, if I am doing it with a refrigerant, my L should be equal to 40 millimeter, roughly 4 centimeter, or how many inches is that? Well, yeah, let's say 1.5 inch. So now you go back and look at all these papers in the literature where they used a 1 centimeter by 1 centimeter heater. Okay, then the question becomes, is it justified? Okay, and I am going a little ahead of myself, but I will show you, tomorrow, that when you make a nanostructured coating, the bubble diameter at departure, with nano coating becomes almost 1/3 of the bubble diameter at departure without coating. Okay, so typically the bubble diameter at departure for a refrigerant bubbles is about 900 microns, or roughly about 1 millimeter, right? The moment you make a nano coating, this becomes about 300 microns. That's what the experiments show. What that means is, that means your Taylor instability wavelength is going down by a factor of 3. Okay, now the question is why? We are going to discuss that tomorrow. Okay, but at the basic here, what you see is the lambda d for nano coating then is approximately 1/3, isn't it? So if I have a 1 millimeter by a 1 centimeter by 1 centimeter heater, okay, without coating, what is the value of my L prime? Okay, so L prime I am defining is as L by lambda d. So if this is 1 centimeter and I know my lambda d is 8 millimeters, that's approximately 1.25, right? That's definitely less than the value of 5 that Lienhard and Dheer have suggested. Now let's look at the situation where you have a nano coating, L prime for nano coating. Well, this is still 1 centimeter, but now this has gone down by a factor of 3, isn't it? How much am I getting? About 3.75, roughly about 4. So it's very close to the large heater limit. Okay, so the same experiments that you see in the literature, for the plain heater, it's definitely a small heater, and the nano coating one is very close to the large heater case. And you are looking at these two and you are saying, oh, I got an enhancement of this much. But you are not comparing apples to apples, you are comparing apples to oranges. Okay? And that's the fundamental flaw in the boiling literature in the last 10 to 15 years. Okay? People blindly did experiments without caring for the theory. Okay? So it's good to be aware of the theory before you start doing your experimental design. Does that make sense? Yeah? Okay? So that's the large heater, small heater limit, discussion. Let's see. I guess it's about 4:30, so we can do some tutorials now. Oh, 4:40. So let's take, well, I mean, we are already past the limit. So let's skip the tutorial to, well, let's do one tutorial and then we can call it a day. How about that? Do you all agree? Okay. So let's see. So let's go ahead and calculate the maximum heat flux at 1 atmospheric pressure on a large cylinder. on a large I am sorry heater. Okay. So, what did we say was the value of the maximum heat flux? Let us recap. Can somebody tell me what is the equation? Flat plate, yeah. Come again? No, no, not the UGC. Yeah, C1, right. C1 times rho g times HFG, sigma times G. Okay. Is that what it is? And there is another constant, right? What did we say? Oh, CF, right. So, how much did we say was the correction factor? 0.12, and then how much was it for lambda c? 0.16. So, we can take the average of these two. How much does that come out to? 0.1, 0.14, right? Okay. So, let us assume it is 0.14 times this whole thing. So, how much is rho g? We said it is about 0.5, right. How much is HFG? It is 2.257 times 10 to the power 6. Sigma was 50 times 10 to the power minus 3 newtons per meter. This is joules per gram, this is kilograms per meter cube. Anything else? I think that is all we need, right. Okay, so, let us go ahead and calculate and see how much we get. I am sorry, C1 is approximately 1. Anybody has a calculator? Can we do a quick calculation? I thought it was rho L minus rho g square, right? Isn't there a square there? I am sorry, what's that? One more term? What is that? So, rho L plus rho g square or rho L minus rho g square? Well, I have to look it up now. So, there is one more term here, rho L plus rho g, right, to the power of, well, this is approximately 1 anyways, you know. So, .1145 watts per meter square. Do you all agree with this number? Anybody else got a different number, or you are getting about the same number? watts per meter square? Kilowatts per meter square. Who said 1145? Oh, I heard 1145. Okay, 745, right? What's that? Yeah, it should be per meter square. Is everybody else getting the same number or? All right, in that case, let's call it a day. All right. So I know some of you had questions, so I can answer your questions now. Okay.